Okay, so starting section 3, accuracy versus precision. And both are important, when, especially when we're doing labs, when we're calculating and things like that. Accuracy, short term to me, is close to right. So I need to know the right answer to know if I'm accurate. It refers to how close a measured value is to an accepted value. Your accepted value is the right answer. So how close to being right are you? Precision refers to how close a series of measurements are to one another. So here's the bullseye's where I want to be, so that would be accurate. Obviously, this is not accurate because it's not near the bullseye, but all three are close together, so that would be precise. They're very close to the same, but it's not right. Here is what I would really like to have all the time. Precision, so all measurements close together, and you're in the right area. And this poor person obviously shoots arrows like I do. They're not accurate, nor are they precise. They kind of just go all over the place. Another example, when we look at tests, your test score, if you get a 90%, 95%, you're pretty accurate. If you take your tests and you have 5 tests and you got a 62, a 65, a 63, a 64, you're pretty precise. You're pretty precise. You do about the same, but you're not that close to accurate. So precision doesn't have to be right. The other example here, if I don't calibrate my scales, you can use one of my scales and get 8 grams, 8 grams, 8 grams, and maybe the right answer is 11. So your scale's not accurate, even though it's giving you the same number all the time. So accuracy is correct. Precision just means that you're close to the same all the time. And I am going to show this one.
Exactness of a measurement is called its precision. Precision depends on the instrument and the technique used to make the measurement. Generally, the device that has the finest division on its scale produces the most precise measurement. The precision of a measurement is 1/2 the smallest division of the instrument. For example, the graduated cylinder has divisions of 1 ml or milliliter. You can measure an object to within 0.5 ml with this device. Hence, the reading from the instrument can be precise up to 0.5 ml. The smallest division on the beaker is 50 ml, which makes its precision 25 ml. Accuracy describes how well the results of a measurement agree with the real value. That is, the accepted value as measured by competent experiments. A common method for checking the accuracy of an instrument is called the 2-point calibration. First, does the instrument read 0 when it should? Second, does it give the correct reading when it is measuring an accepted standard?
And that is something that is something that I check. So when you guys use my scales, you're going to assume that they're correct. So, and obviously I needed to check my one because it was off a little bit. What I want to point out, so if I have a graduated cylinder, and here it's 50 milliliters, and here, did I call this a graduated cylinder? When I have a beaker, it's 50 milliliters. When I have my graduated cylinder, I have a milliliter. So by looking at these devices, which one's more precise? The graduated cylinder. This is the device I want to use to be the... If I tell you to get 100 milliliters and you measure it to this line, I guarantee when you pour it into the graduated cylinder, 99% of the time it won't be exactly 100. So the more lines something has, the more precise it'll be. So when we are measuring things, that's something that will be important. So in the lab, we are pretty much always going to have error. Very seldom does something happen perfectly. So error is defined as the difference between experimental value and, again, the right value. So if here's my lab situation. I've got Royce, I've got Renee, and I've got Adriana. And I've got, Abby didn't put hers up there. So I have my information. Here's the density that student A got, student B, student C. Notice that none of them got the same answer. And when we do that in the lab, you guys don't get the same answer. So you are going to be off. So they were off by 0.05 below. This person was 0.11 above, so they were off a little bit. The only way that you know that is if you know the accepted value. And here, we don't know it does not say the density. Oh, yep, it does, right here. Here it tells me the density. So this is the accepted value. The accepted value will have to be given to you. It's the right answer. So if we do a lab and I tell you to find the density of aluminum, the only way you can calculate your error is if I give you the correct answer. What is the density of aluminum? And to do this, it's very much like grading a test, other than if you take a test and you get a 95%, you have 95% what? Right. Correct. Your percent error is 5%. So in chemistry, which makes us sound a little like Debbie Downers, I don't want to know how much you have right. I want to know your percent error. I want to know how far off you are. So in order to calculate your percent error, the equation is experimental value minus accepted value. Notice it's absolute value. So in all honesty, you take your bigger number minus your smaller number. It doesn't matter on the top which one's which, because it's absolute value. But on the bottom, when you divide, it has to be the accepted value. So for example, let me see if there is an example. Yeah, perfect. So I don't have that table in front of me anymore. Students' density data in table 3. Can you guys read it? I know it's small. Yeah. Okay. So students' A density in table 3, what was it? 1 point something, I assume.
Negative 0.05.
That's the density?
No, it's 1.54 grams per centimeter.
Okay, that sounds, okay. So 1.54 grams per milliliter. So that's what the student found in the lab, measuring stuff, using the graduated cylinder. That's what was found in the lab. At the top of the table, it tells me that 1.59 is the right answer. That's the accepted value. So to use my formula, I'm going to simply take my bigger number minus my smaller number, and I'm going to divide that by which one? 1.59, because that is the correct answer always goes on the bottom. And then to change it to a percent, I will take it times 100. Which if I look at that, 1.54, 1.59, student did a pretty good job. It's pretty close. And there you calculate. So when they calculated, you get a 1.26% error. In the chemistry lab, that's fantastic. Sometimes we will have a 40% error. The way that you get this as low as possible is you're precise with your instruments. You read your graduated cylinder very carefully. You measure with a ruler very carefully. We want to keep that percentage as low as possible. And I think that's where I want to stop anyway. Yep, that's where I'm stopping. Significant figures we'll talk about next time.